Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistance, and today we are looking at two different concepts that relate to phase change. One of them is vapor pressure and the other one is the energy needed to heat something. So let's start with the first one. We're given that the vapor pressure of ethanol at 20 degrees Celsius is 5.95 kilopascals. We're asked to calculate the vapor pressure at 50 degrees Celsius. So the first thing we're going to want to do is convert all these Celsius temperatures into Kelvin. So we're going to call this one T1, and T1, 20 plus 273 Kelvin is going to give us 293 K. And we're going to call this one T2, and that's going to be 50 plus 273 is going to give us 323 Kelvin. And for the pressure, we have 5.95 kilopascals, and you would need to look up the heat of vaporization for ethanol. This should be provided in your book, and I will go ahead and write down what it actually is. So our heat of vap, HVAP, is going to equal 39300 joules per mole. And you can look that up relatively easily. So, given this information, where do we proceed? Well, the best way of proceeding is using what formulas we have available to us. And there is one that utilizes heat of vaporization, two different temperatures, and two different pressures. And we're wanting to find pressure number 2. So that formula is the natural log of pressure 1 over pressure 2 is equal to the heat of vaporization over our R constant, which is the gas constant, times temperature 1 minus temperature 2, all over temperature 1 times temperature 2. So let's plug in the values that we have. Edit. So we've got natural log of 5.95 kilopascals over P2 is equal to 39300 joules per mole over 8.314 joules per Kelvin mole times 293 minus 323 Kelvin, all over 293 times 323. And that is going to give us, at least for the right-hand side, is going to give us a number. So for the right side of the equation, we find that the answer is going to be negative 1.49842. I know that's a little bit beyond sig figs, but we're going to hold it just for now to get a more accurate answer. Because if we were to want to isolate P2, we're going to have to take everything to the e to the power of both sides. And e to the power of a natural log is simply the stuff within the natural log. So we end up with 5.95 kilopascals over P2 is equal to e to the negative 1.49842. And then isolating P2, you simply multiply P2 to both sides and then divide by e to the negative 1.49842. So we end up P2 is equal to 5.95 kilopascals all over e to the negative 1.49842, which gives us 26.6 kilopascals. And that is the vapor pressure at 50 degrees for ethanol. Now, our next problem asks us to calculate the amount of energy needed to heat 500 grams of water from negative 20 degrees Celsius to 180 degrees Celsius. And it gives us the specific heats as well as the molar heat for fusion and vaporization. And this is just a simple thermodynamics problem. All you need to do is recognize that Q is equal to M mass times the specific heat times the change in temperature. And we can keep temperature in terms of Celsius in this case. We do not need to convert to Kelvin because our specific heats are given in terms of Celsius. We are going to want to make sure that all of our units match up in the end. So definitely keep track of your units. And ultimately, this is a multi-step process. You kind of think about it like a roadmap almost, where at negative 20 degrees Celsius, you're in ice. This is water. Water is in its ice. It's its solid form at negative 20 degrees Celsius. So from negative 20 degrees to 0, it's going to remain in ice. Then at 0, you're going to account for the fact that it's melting. It's changing from ice to water, liquid water. So it's going from a solid to a liquid. So that's the second step. The third stage is going to be going from 0 to 100. It's liquid water that whole time. And so you just account for that change in temperature. Then at 100 degrees Celsius, it goes from a liquid to a gas. It goes from liquid water to vapor. Steam is what we refer to it as. And so you're going to want to account for the vaporization of water at 100 degrees Celsius. And then from 100 to 180, it is steam, and you're only accounting for the change in temperature. So there are two types of equations that we're going to deal with. One of them is Q is equal to ms delta T. The second equation that we're going to deal with has to do with simply relating the mass with the number of moles of the molar heat of vaporization. Okay? And converting that mass to moles so that we can account for it. So it's simply going to be a unit dimensional analysis converting 500 grams to moles and then multiplying that by the molar heat to get the total heat that is used to vaporize or to melt. Okay? So the first thing we're going to do, we're going to call this Q sub 1. There's going to be 5 Qs in all of this. Okay? Q sub 1 is going to equal 500 grams times our specific heat of ice, which is right here, 2.03 joules per gram degrees C. So 2.03 joules per gram degrees C. And then multiply that by the change in temperature from negative 20 degrees to 0. So that's going to be 20 degrees Celsius. That's our change in temperature. So that's going to give us 20,300 joules, or if we convert to kilojoules, it's going to be 20.3 kilojoules. So that's the first leg of our journey. Second leg, we're converting solid water to a liquid water by using our molar heat of fusion, which is edit. We're converting solid water to liquid water using the molar heat of fusion, which is right here, 6.02 kilojoules per mole. So for this, we're going to take our 500 grams again, because the amount of water, the mass of the water, does not change. What's going to happen is essentially the moles are not going to change. So we still have the same amount of water no matter what we do. So we're going to just convert that to moles. 1 mole water is equal to 18.02 grams. That's H2O. That's 16 plus 2 times 1.008, roughly 18.02. And then we're going to multiply that by the molar heat of fusion to find out how much energy was actually expended to melt the ice. So that would be 6.02 kilojoules per mole. And we don't have to convert to kilojoules in this case because it's directly relating to kilojoules. And that gives us 167 kilojoules. That's quite a bit. Then, so this is Q2. For Q3, we're going up from 0 to 100 degrees Celsius. So our delta T will be 100 degrees Celsius. And we're still dealing with 500 grams. And our specific heat for liquid water is 4.184 joules per gram degree C. So 4.184 joules per gram degrees C. And then our change in temperature, as I previously stated, is 100 degrees Celsius. And that gives us a total of, looks like 209 kilojoules. Or if you were to do this in joules, it's approximately 209,000 joules. But again, we want all of our units to be the same, so we're going to keep it in kilojoules. If you did the calculation directly, it would equal approximately 209,000 joules. All I did to get it to kilojoules was divide the joules by 1,000 to get kilojoules. So for Q4, we're converting all that liquid water to steam. So again, we're going to take 500 grams and we're going to multiply it by 1 mole over 18.02 grams. And we're going to want to multiply that by our molar heat of vaporization, which is right here, 40.79 kilojoules per mole. So 40.79 kilojoules per mole. And that's going to give us 1,130 kilojoules. Our fifth and final leg of the journey is to convert to account for the change in temperature from 100 to 180 degrees Celsius. So again, we're going to use our Q is equal to ms delta T. So 500 grams times our specific heat of vapor or steam in this case, which is 1.99 joules per gram degree C. Times our change in temperature, which is 80 degrees C. 180 degrees Celsius minus 100 degrees Celsius gives us 80 degrees Celsius. So that would be, if you convert it to kilojoules, is 79.6 kilojoules. If you left it in joules, the direct calculation will give you 79,600 joules approximately. So we've got all the legs of the journey. Now we just need to sum it up. So our Q total is going to equal Q1 plus Q2 plus Q3 plus Q4 plus Q5. So basically all you're doing is you're adding this all together. You're adding all 5 of those numbers up. What that gets you after you've summed them all together, you get 1,608 kilojoules approximately. And that is the amount of energy needed to heat 500 grams of water from negative 20 degrees Celsius to 180 degrees Celsius.